I'm showing this slide as an opening slide because it indicates from the 1950s and early 1960s the fallout in terms of the radioactive iodine pickup found in thyroids 20 to 30 years later. It was done in 1993, and it was tracked with the thyroid cancers in the United States. As you can see, the top of the map has a straight line. The attempts to map fallout in Canada were, it was attempted, but Prime Minister Trudeau at the time said, no, we don't need to know. So while we are absolutely confident that the 49th parallel was not sufficient to stop radioactive drift into Western Canada, and especially two other areas across the Lake Ontario and up into the Quebec regions. The pink and red are the highest fallout areas. There are other maps on the site if you're really feeling like looking at different radioactive fallouts by just going to nuclear fallout and Google it. Pictures of nuclear fallout will get you there even faster.
When was the fallout measured, though?
The fallout was actually years later. Years later.
Why didn't they measure I-131 with a half-life of 8 days?
Because you take that times 10, and you still wind up with some radioactive iodine in thyroids. It really was an amazing study.
Did they measure it by scans?
You know, I'm not exactly sure how the measurement was done. Yeah. So I thought, did they measure by scans? And I'm not actually sure how the measurement was done. I wasn't party to the actual measurements. An attempt in 1997 was made to follow up in solid cancers, and they follow up with solid cancers did not occur. There's no real reasons given, but many of us can assume that there were that much of the reasons were political, maybe cost as well. I use this one to indicate the fallout from Chernobyl because we're now looking at something that's more than 25 years after Chernobyl, and the fallout, cesium-137 was the initial radioactive element detected in 1986, and those were the areas that it was in which it was detected. So there's no doubt in my mind that between radioactive nuclear weapons testing and nuclear power generation, we are making the world a more radioactive place to live in. So
yeah, we can. Those are the levels in '86, because it says 2009, but that's just when the publication.
That's when the publication was made. I've said that this is the ionizing radiation and health talk for medical students and generally and the general public. So I will probably be able to, in this small group, skip over some of the earlier definitions which talk about the radioactivity. My faculty or personal disclosure is that I have a book that's available at the Physicians for Global Survival desk, from Hiroshima to Fukushima to you, on all of the aspects of ionizing radiation. And I am shamelessly promoting it. So I presume that that would be what's meant as a conflict of interest. So what is radiation? I can skip through this, I'm sure, because now I know what it is. What is ionizing radiation? And Gordon Edwards has suggested that we quit calling ionizing radiation radiation and refer to it specifically as radioactivity. And part of his reasoning behind that is that radiation is the transfer of energy, while in much of the cases, in the case of the particles, beta particles and alpha particles, we're not transferring so much energy as we are transferring particles. And particles contain the energy that makes the difference in the long-term physical effects. Oh, I finally figured this one out. This is a picture of what happens when one ionizing ray passes through a cell. It knocks off an electron, forming an ion, whether that's becomes a different, and generally speaking, that means it's either positively or negatively charged ion, and then can unite with other particles and change the way and the molecules are built and the structures in the body, if we're talking about organic molecules, work. I'm sorry, I'm having a little problem with the shifter here. So, we talk about the ways in which the cell may be affected. And this simple triage effect talks about the repaired cell, which in the perfect world will be repaired perfectly. There will be no damage and no effect to the body. The cell may be dead, which generally speaking may also be no effect on the body. The body just removes it. And then there's a bigger problem that occurs in the mutated cell. Now, we do not know what percentage of cells will fall into each of those categories. But the mutated cell then may have two different possibilities. The cell function may be such that the rest of the body takes it over. There's no problem. It's mutated, it can't do anything, it just sort of grows along and may eventually die, but it's no longer functional, but some other cells can take over the function. Or it may multiply and form cancer, a cancerous cell, because it's been altered. Or it may be transferred as a genetic cell, a seed cell, sperm, or eggs, and produce a hereditary effect on the descendants. We know that in areas with higher radioactivity, there's higher incidences of Down syndrome. We don't have good data on other syndromes. Let's see if I get this one right. No, I got it wrong again. There's a 50-50 chance I will make this little dial go the wrong direction. This is my assistants, research assistants, just drawing of a double strand and a single strand DNA injury. And of course, with a single strand DNA injury, the bases on the opposite side, or the opposite side of the DNA, can replicate their matching pairs. When you have a double-stranded injury, however, the break on both sides means that you have a permanent injury. This is the type of injury that can go on and produce the genetic effects that we mentioned. The two pieces can join to incorrectly, may join to other DNA molecules, or may actually produce or actually fail as a genetic module. It's a lost gene. I'm often asked, well, how can the industry say that 100 millisieverts is safe, that they have seen no effect on human health from 100 millisieverts. The Canadian Nuclear Safety Commission has that line, and they stick to it.
Is that 10 rems? 100 millisieverts. 10
I
rems.
don't know how to translate rems to sieverts. So, sorry. Is
10 rems.
100 millisieverts 10 rems? Does someone else know how you translate the two? I don't, because I've only ever worked in millisieverts or sieverts. In any case, when people ask me how the CNSC can make that statement, I go back to this. Alice Stewart published in the British Medical Journal in 1958 a epidemiological study where they were looking at leukemia and doing an extensive questionnaire, household questionnaire on people in the area, whether or not they had offspring with leukemia. So they're looking at everything. They're looking at smoking in the household. They're looking at numbers of people in the household. They're looking at whether or not their mother is working. They're looking at the diet in the household. They were looking at socioeconomic factors. And the only factor that they found that indicated a risk for developing leukemia in the newborn was if the mother had had a chest x-ray during her pregnancy. One chest x-ray during pregnancy increased the risk of cancer in the offspring by 3. She was almost immediately vilified for her research, but I think with the exception of 2 people in this room, we're all old enough to remember putting our feet into fluoroscopes and having in every store and having our foot measurement taken. And some of us will remember having your annual children's chest x-ray for screening for TB that occurred in Canada. We don't know exactly what that has done to our longevity in terms of cancer cells. Nobody studied it. But since nobody was really taking Alice Stewart seriously on this side of the Atlantic, Rosalie Bertell was also asked by the Tri-State Leukemia Study to do the same thing in the United States. And they actually enrolled 16 million people over a period of 3 years and ended the study in 1962 and replicated the numbers. Same type of study, same epidemiological scan, same connection, and same results. Hers was published in 1965. And over time, we who were in the medical profession or studying at that time started to notice that we were no longer doing or invited to do chest x-rays or x-rays of pregnant women at any time. In 1976, I was still taught in medical school to do pelvimetry, which was 3 views of the abdomen, which would have directly irradiated the fetus in order to see if a woman had a large enough pelvis to deliver babies. In fact, there was no correlation anyway, and it was already sliding out of style, just as the nuclear power plants are sliding out of style at this time. The likelihood, and so very few people were doing it, and as I recall, the only x-ray I did of a woman in pregnancy was to determine whether or not the breech baby had an extended neck, meaning and could or could not be delivered in our regional hospital. Okay, so the one thing that is transmitted from as energy that would be considered radiant energy is the gamma ray. And the gamma ray emits energy similar to that of X-rays, but it is extremely specific to any given element. And it is the most commonly used medical radioisotope emitting radiation, because well, I'll get to that, sorry. The substance that emits the gamma rays can be implanted, injected, or ingested. And then literally what we do with the patient is we can put them over what would be the equivalent of a photographic film, in this case a gamma camera, and in the photographic film element they just simply light up the parts of the body where the radioisotope will have gathered. So the definitions, which I really don't know if I need to, but I'll do quickly. Radioisotopes are various forms of the same element with different atomic weights, the same atomic number, a lot like dogs can be collies or spaniels, but they're still dogs. Radioisotopes are isotopes that are radioactive, and radiopharmaceuticals are the ultimate designer drugs. They are fashioned by combining a radioisotope with another molecule that can be specific to the imaging or the treatment desired. The most commonly used radioisotope in imaging is technetium-99M. The M means it only releases gamma rays. In Canada, it was the big deal in 2007 and 8 when Chalk River was shut down by the regulator because of safety issues, and was restarted in spite of the fact that the safety issues were not addressed, because our Prime Minister, who did not know much about nuclear safety, said it has to be restarted. So I use that a little bit as an example of how people who know nothing about the system can endanger the health and welfare of people around it. The technetium-99 can be attached to various other molecules that have a predilection to go to those body parts. So I didn't go into medicine because I could say words with more than 3 syllables. So pardon me if so we have the 3 examples there. We've got exametazime for brain scans. We've got cestamide for myocardial scans, and you may have heard of MIBI scans, and mercaptoacetyl triglycerin for kidney function, because those parts of the body will be attracted by those particular other elements, which those parts of the molecule are not radioactive. The technetium-99M is. Radioactive decay is another issue. Everything that is radioactive means it gives off its energy, either in particulate or radiant form, and then becomes another element. I use this to show how many elements you can get out of one particular radioactive element. We've got uranium-238. This is the uranium-238 decay chain, so it actually is a bit of a misnomer to call it the uranium decay chain. As you notice, it doesn't have uranium-235 in that decay chain because it's not part of the uranium-238. Uranium-235 has a decay chain of its own. The uranium-238 gives off an alpha particle and becomes uranium-235. Then it gives off a beta particle and becomes protactinium-235. So the decay chain is almost always written so that you're coming down the chain is giving off an alpha particle. pardon me, you'll notice in the middle of it we have a gas, radon 222. As long as all of this is locked up in the soil, the gas is widely dispersed. When we take it out of the soil and leave it in tailings, for example, this decay chain goes on and the gas is released to the atmosphere. Another example of increasing radioactivity. The gas is short-lived, so it continues the rest of this decay chain, and we get polonium-210, one of the most toxic substances on the Earth. The size of a period on a piece of paper will kill a person, and has done so. The Litvinenko, the Russian spy that was was killed with polonium-210. This is just another example showing the very short start of the uranium-235 decay chain. And here you can see that the different lengths of times of decay can be very short, like the thorium-231 is 1.06 days, protactinium is 32,000 days, and our good old uranium-235, the one that we use in our nuclear power plants, is a good 703.8 million years. So the ideal, and I will come back to whether or not how ideal this might be, the ideal gamma-emitting radioisotope would have relatively low energy gamma emissions so that it has less damage occurring, has a very short half-life, or at least a half-life long enough that the images can be obtained, have a short biological half-life, meaning that it goes through the kidneys or as expired or pooped out, or however it is removed from the body, so that if this is the ideal one, we have at least one of them, which is the iodine-123, used in 3 places: SPECT scans, contrast CTs, and MIBG scans, which are for the heart. Once again, gamma rays. Brachytherapy is when particles of radioactive substance are placed in the cancers. The commonest ones that we use it in medicine in Canada are in localized tumors of the breast and prostate. But it can be used in other tumors. They're doing experiments with it right now in pancreatic cancers. When they talk about using it temporarily, it is used like for bladder cancers. A radioactive substance is placed into a catheter that then the balloon is blown inside of the bladder, and then it's left in for 4 to 6 hours, depending on the patient's tolerance and the amount of radioactivity that they want to have delivered to the tumors in the bladder. Normally, when they are put into prostate, they are removed. They are never removed. And when they're put into breast cancer, sometimes it's used by a needle process, where the needle is left with a wire sticking out of the skin, and then the radioisotope can be removed after a given length of time. Common ones use cesium-135, cobalt-60, a little bit falling out of practice. Iridium-192 is currently the popular one for prostate cancer, iodine-125, and palladium-103. And a bit of a concern is that when they do decay, and the decay substances are, of course, left in the body. Cesium-137 decays by beta particle emission to barium-137, And then we have some that are used that are alpha particles. This is just a little sideline on what, in fact, an alpha particle looks like. And it's the nucleus of a helium atom, 2 protons, 2 neutrons, and it's generally considered large size, so slow-moving, and of poor penetrance. And when I went to school, they said it was perfectly safe. Nuclear regulators still say that alpha particles are your skin, stopped by your skin, stopped by a piece of paper. Yesterday we heard from someone saying that the people selling the idea of uranium mining put it on their face, on their cheeks, and say, look, I can do this. It's it's alpha particle. This is just fine. I can put it on my face. I'm not going to have any damage. However, this is a electron photograph of an alpha particle lodged in a rat's lung. And as you can see, the energy is going out to all the cells around it. It's highly exposed. It's considered 20 times more radioactive and more serious in terms of biological health of the cells. It has been used in brachytherapy in the past, especially the radium was an alpha particle. And it was probably, and radium 226 was our first implantable particles. This is radiation weighting factor, which is the measure of the potential to cause damage. And I've already said this, 20 times higher than beta particles and gamma rays. Another view of the chain. A beta particle is really an electron that has the ability to penetrate skin and soft tissue to about 2 to 4 centimeters. But depending on the energy, because each one of these particles has a different energy depending on the element from which it comes. And those are just examples of beta particles. I'm not sure why those guys, my uranium decay train keeps creeping in. So this is a rather complex little list of the sources on one hand and the radiation dose received on the others. Now, many dental offices have gone from X-ray with a digital outreading, and the digital X-rays use slightly less radioactivity, expose you to slightly less radioactivity than the older X-rays that used film. So if you're getting your X-rays done without having a piece of a bite wing film piece put into your mouth, you may be receiving less than this. The airport passenger scans, which are done, I think, still only in the United States, although I've seen scanning boxes in Canada, do give you radioactivity, so the choice of it. But when we get down here, take a look at the amount of radioactivity from the PET studies, average out at 14 millisieverts, smoking at 53 millisieverts per year, if that's a pack a day, and the nuclear cardiac test is 10 millisieverts for one test. Many of our cardiac victims have several tests during the process. These, the X-rays may decrease slightly since they're changing to digital, but where they're using imaging radioisotopes, those are not being decreased. I have a list of the units of measurement, but we've just run into the issue where I can't even translate from one to the other. The older is written in brackets. The sieverts, radiation, weighting factor, grays, becquerels. Nuclear physicists like to use becquerels and talk about half-lives in terms of becquerels. So if you have, while lay people like myself, or not nuclear physicists rather, prefer to just simply talk about the number of atoms that will have decayed during a given piece of time. There are two more ways of measuring it. We have the amount of radiation emitted from a source, the amount of energy that's absorbed by the target. This one is a converting factor. The actual dose, expressed as in the amount that can do damage. And then there's the effective dose, based on the response of a biological tissue to it. And finally, we have the committed dose, that will be the biological dose received from materials inserted and or embedded. And by or embedded, I'm thinking of shrapnel, especially in Iraqi veterans and victims. Did I just go backwards? Yeah, I did. I went backwards. Yeah. No, I didn't go backwards. So I'm going to close this on my three concerns with medical radioisotopes. My personal view is that in about 100 years that we've peaked in the last century in our use of radioactivity, both as imaging and as treatment, and then in another 100 years we will look back on that century as the same way we look back on bloodletting in the distant past. But there are two very good studies on iatrogenesis. There is another study on cancer in children from CT scans that's in the United States, but it's not particularly well done, so I don't include it in here. It, however, raised an alarm, and you will not see as many CT scans being done in children now as in the past. However, there is according to the Canadian Medical Journal, there is an estimated 8% of secondary cancers due to radiotherapy for the first cancer. So you got cancer, you get radiotherapy, you develop a secondary cancer. Fully 8% of the secondary cancers are due to the radiotherapy. And then this was done by the University of McGill in Montreal, and they found that for every 10 millisieverts of exposure, you had an increase in 3% of cancers in the following 5 years. And we're talking about cardiac scans that we have been doing by the dozens. You have a minor heart attack, you'll be sent for a cardiac scan, and you will not get actually you do. As you're going in to get injected, they will talk about the exposure to radioisotopes, but they will not talk about the percentage of injury that you're going to get. I was offered one for minor chest pain. I cannot believe that they did not give me any risk factors ahead of time. I didn't take it. It was, I thought I knew why I had a chest pain anyway. Then we have another little problem. All of the radioisotopes that we're using decay. So if we look at the most popular radioisotope, the technetium-99, which decays, technetium-99M rather, which decays, loses its M, and takes 240,000 years for the technetium-99 to decay. So you've just gotten rid of your low-grade gamma rays. Now you have 240,000 years of the technetium-99, which is a man-made product, for it to decay.
Is it gamma?
No, it decays by beta. And so it is removed from the body by a 95% is gone in the body by 24 hours. So it has a fast biological half-life. However, that means it's been peed out, pooped out, or respired out into the environment, and so we've increased it. Another way we're increasing our radioactive body waste. And then I have in small letters, because I could not find any reference to the fact that during the production of the radioisotopes that we use in medical science, we must be producing other less desired radioisotopes. And I cannot find anything about how or what they do with them. So, by the time I finished, I now know how to move the slide backwards or forwards. So, thank you, and I can take some direct questions, but maybe we'll let Helen respond to what I've. Oh, she doesn't want to. Okay, not right now. Okay, we can answer questions for you.
Two questions. First of all, thank you for a nice presentation. I was told that mammograph was very safe when I was a student, and that can be done even in the pregnant ladies because it just targets soft tissue, and it can detect actually if the cancer has already started 2 years. So when we do serial mammographies, does it increase chance of cancer by itself because every 3 years, every 5 years, just need to follow up?
The early mammograms were probably responsible for about 5% increase in breast cancers. Now, I don't know if anybody has any research on what's happened on the more recent ones. I read a figure that 1 in 40,000 breast cancers will be caused by radiating the breast. I think that in a few years we're going to see mammograms fall out of style because the United States studies have indicated that using heat detection, what is that called? Thermography is more accurate and is of much less danger to the woman's breast in the long run. Currently in my own practice, I cut back a lot on mammograms by taking the people out who are just coming in because of fears, the young people whom we can't feel a breast cancer and their incidence of developing breast cancer is very low to start with, and even their history is unlikely to produce breast mammograms. So I think it's important to address that.
When they do this kind of imaging that's involved with radiation, especially when they use radioisotopes, they try to hydrate patients to actually eliminate the elements faster.
Yeah.
But as I'm guessing, especially for the cardiac imaging that you mentioned as the major radiation, many of them have heart failure, so it might be worse.
Yes, very good point. In fact, I'm going to repeat that for the tape, and that in most injectable radioisotopes, the patient is well hydrated so that the radioisotope will be eliminated faster. This can't be done for a large number of cardiac patients because they are already in heart failure. Good point. Yeah, you have to do it here, that's all.
Well, Dale knows much more about medical isotopes than I do because I haven't practiced medicine per se for a long time. But what worries me partly is that when we inject patients with isotopes and they eliminate them into the sewage system. Or they go home and they eliminate them via urine or feces, but other people could become contaminated, and anyway they go into the sewage system as technetium, as Dale said, which is a beta emitter, which is pretty dangerous biologically, has a hell of a long half-life. So we in medicine are adding to background radiation in that way, although it is very useful to use isotopes in many areas. I think also for mammograms, they used to use older equipment and doses were really quite high. And I've got a friend who's a physician who's 52, brilliant woman, who's just been diagnosed with breast cancer triple negative. And I'm sure she's had lots of mammograms in the past. The breast is a very radiosensitive organ, such as little girls in Hiroshima and Nagasaki who had no breast tissue, just a nubbin of cells to produce breasts later, had a higher than normal incidence of breast cancer. So we know the breast is a very radiosensitive organ, and so we X-ray it. So there are a lot of questions that we have to answer in medicine, and we have produced in the past a lot of disease because of our ignorance, and we learn as we go on about what happens to patients. The other interesting thing is, well, too interesting, my ex-husband was a radiologist. He was pretty careful, wore his lead apron. He had cancer of the bladder and prostate, and his colleague also was a radiologist. He had cancer of the kidney. A lot of radiologists do develop cancer. And I was going to say something else too, relevant to cancer. And I can't remember what it was. Anyway, we're very didactic in medicine. We're very conservative in medicine. It takes us a long time often to admit we've made mistakes. And that's how we learn, of course. But, you know, it took Semmelweis 50 years to get the doctors to wash their hands when he discovered the cause of childbirth fever. So we are fairly conservative.
Would you like to comment on what we are going to see with increased tritium?
Yes, tritium is a very toxic substance, H3, radioactive hydrogen. Tritium's interesting because the only thing that prevents the egress of tritium is gold, because it's so dense. It escapes from everything else, glass, plastic, steel, the lot. So you can't prevent tritium escaping, nor can you remove it from water. Now, every reactor makes a lot of tritium, and it's always released in the air and into the cooling water and into the water of the lake or the river or the sea from whence the cooling water comes. The industry says tritium's okay, it's only radioactive hydrogen, but if you look at the research that they've done, particularly in the Journal of Health Physics, there's a huge literature on tritium where they've injected it into animals, rats, mice and the like. And tritium is a beta emitter, and because beta is low energy, when it's in the body, all of the energy gets trapped. It doesn't escape through the body out into the atmosphere. And as such, it's very carcinogenic. They say it's not biologically bound, but it is biologically bound in food and also into the body. It doesn't concentrate by orders of magnitude, but it is biologically bound. And it's found to produce brain tumours, fetal abnormalities, and various other cancers in animals. And it's a very scary substance. Now, in Fukushima, they've got a hell of a lot of radioactive water, and they say they can remove the other isotopes, but in fact, I've got a chart on my computer which shows over 200 different isotopes are made in a reactor. 200. I mean, there are about 5 isotopes of tin, for instance, and 6 of silver and the like. And none of those isotopes are ever mentioned in terms of Fukushima and what's in the water. All they talk about is cesium and strontium and tritium. Well, they can partly remove the cesium and strontium, not totally, with ion exchange resins, but there are many other isotopes that are never mentioned, and also they can never remove the tritium. So now what they're talking about in Fukushima is, with all this radioactive water, they think they might just evaporate it, because that's a good way to get rid of it. Heat it, and up it goes into the air with all the isotopes and the tritium. If you live near a reactor and there's an inversion system and it's foggy, you've got tritiated water in the fog. Tritium is one of the only elements that actually penetrates the skin. And so if you're enveloped in a cloud of fog with tritiated water in it, it can penetrate the skin and get into your body. But it also enters the body via inhalation and ingestion. And children are 10 to 20 times more sensitive to radiation than adults, and fetuses thousands of times more so. And there have been numerous studies, a very good one in Germany, one in France and one in Britain, to show that children less than the age of 5 years, living less than 5K from a reactor, have double the incidence of leukemia and a high incidence of solid cancers. The industry has tried to negate those studies, but they're very clear. And that's only looking at children. And it may, but the other thing is that every year they refuel the reactor. They take out 30 tonnes of the old fuel, there's 100 tonnes, and put it in the cooling pools and replace it with fresh fuel. And during the outages, huge amounts of radiation are released. So what they do is average over the whole year that large amount of radiation to show that, in fact, very little escapes. So they lie with data. And therefore, if you live near a reactor and there's an outage once a year, you can be exposed during that period of time to a fair bit of radiation.
Thank you. No, I think so. Well, because I think tritium is one of the bigger issues that going forward from both the accident in Fukushima and also from nuclear power degeneration around the world. Thank you so much. And we're supposed to be closing right now, so